Hello everyone, welcome to Engineers Ireland and the maths grinds that we're running. Today what we're going to cover is the first half of complex numbers. It's the half that looks like ordinary algebra. The second half is the half that looks more like trigonometry because it's dealing with polar coordinates. In this we're still dealing with the same kind of thing in ordinary algebra, where you've got like an x bit and a y bit and you can plot them and do all the usual things. Okay, what is it that makes a number a complex number and has other ones being called real numbers? Now it sounds like it's a much nicer club to belong to the real club rather than the complex club. So where's the difference? A lot of problems that scientists and mathematicians would have looked at for many hundreds of years would have seemed impossible to solve because they couldn't grasp a concept of another or a new form of number. And it's not surprising really, because what happens is we have to use something that nobody, even to this day, still knows exactly what it is. And the basic concept is we're saying for a complex number we will have a real bit, sounds all nice and happy, and we'll have a complex bit, which is the imaginary. It's the bit that makes the number complex, an imaginary bit. So why is it imaginary? You know, it's a bit like imaginary friends don't really exist. So why should we have a number that we're still willing to give the name of imaginary to? It all relates to this, the square root of -1. And we refer to that as I, which is only the first letter of imaginary, so it's very easy to remember this. I don't think that anybody will ever be able to know what I actually is. So let's listen to what that sentence has said, that I don't know what, if anyone ever will know what I actually is. That's a prejudiced viewpoint. It's a viewpoint saying that I think nobody will know it in terms of real numbers, and that's absolutely true. But it is itself. And in mathematics, one of the most important things that we do is we give a name to something. The whole idea in algebra of having x's and y's and z's is we're saying I don't know what the thing is, so I'll give it a name and I'll play with the name as though I know what it is, and guess what? We can figure it out at the end. Here, in order to allow these imaginary numbers interact as in multiplication, etc., with real numbers, what we do is we give it a name to this little guy. Why is it that that is a useful concept? Well, let's step back a little bit. If we go and we look at the usual ax squared plus bx plus c, that function, if I wanted to find the roots of it, and we'll just assume now, and you will be well familiar with this, we're just assuming now this is the y-axis and that's the x-axis, and we'll say I want to find the roots. What are we looking for? We're looking for that guy and that guy. We're looking for where the function has a y value of 0. That's why, if that is the function, to find the roots, we set the f of x equal to 0, which implies ax squared plus bx plus c equal to 0. Now then, let's look at another function. And in a way this is probably reasonable revision for you of stuff that you'd have covered when we were dealing with algebra. In this one there is, now you're supposed to imagine I've drawn a very nice parabola here, because these quadratic functions, they are parabolas. In this particular one, the two roots are identically the same. But what about this equation? This function. What roots does that thing have? Well, as it turns out, it can't have a real root because it would have to touch the x-axis. So we have to have a different form of solution for this particular thing. Now it's very strange that even for a function like this third one down here, if we set that particular function equal to 0, and we know that there is no answer to it, okay, see, it doesn't cross the x-axis, there's no answer to it. The odd thing about it is we still can get solutions to this problem. And probably because it is, in a way, kind of a farcical or silly thing to do, to look for where this function crosses the x-axis when you know it doesn't cross it, you can't be particularly surprised to find that the kind of numbers we get out from it are not the normal, usual, regular numbers. So then, what you've been doing since certainly second year is you'd start with that general form for the quadratic, and you'd say that implies then that x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. And just a little recap for you, that is the same as saying minus b over 2a plus or minus the square root of b squared minus 4ac all over 2a. So what we're saying is that there is some location here, and it is x equal to minus b over 2a. That's the common bit. See both roots here? They have a common bit, which I've shown there. And there is how far the two roots are away from this. One is up, heading in the positive x direction, and the other one is heading down. So that amount here is that. So a root is the common bit plus the blue bit, or the common bit minus the blue bit. And you can clearly see that in the second example that we have here, the blue bit is 0, and that's why to find a common roots, and if we're asked to look for it, we will look for b squared minus 4ac equal to 0. Now, where do problems come in? They come in with these kind of ones down here. And how we solve them is by bringing in a new form of number. Let's say we have a function and we want to find roots to this. We can start with our a x squared plus bx plus c equal to 0, which implies the x equals minus b plus or minus the square root of b squared. Now, I generally have a habit when there are supporting equations that I require, like these things, I have the habit of putting them on the right hand side so as to inform my mathematics, which is the solution of the problem, which will generally runs down along the left hand side of the page. So in this case we're saying that implies x is equal to minus b, which is going to be 6 because it's minus minus, plus or minus the square root, and we're saying 36, is this correct, minus 4 by 1 by 1. Now the real thing I want you to see is over 2a. Look at what's happening in here. We're all quite happy in here because we have a 36 minus 4, and that's going to be positive. Okay? Now then, let's look at for the roots to this one. So then, square root of a negative number. And this is the crux of the matter. What is the square root of a negative number? Well, we really can't express it in terms of a real number, so we have to come up with and understand that there's another and a new form of number that we're looking at now, which will be related to these things. Now, as it stands, you can see there's the square root of minus 27 here. There are many, many more examples. There's an infinite number of examples. And that's a little bit unmanageable. Now, we can turn this into a much more manageable situation if we recognize something. And that is, we could say, well, let's have that equal to a half plus or minus the half by the square root of, and now we'll say 27 multiplied by minus 1. And we know the square root of a by b is the square root of a by the square root of b. So I'll say it's equal to a half plus or minus the square root of 27 over 2 by the square root of minus 1. And I can give a name to this guy. What's the advantage of having done this? So there's the I. The advantage is, now technically I'm using a unit of length 1 in the imaginary side of things, but it means that we're only ever looking at one particular imaginary number, the unit imaginary number, because this number in front of it here, that's a real number, the same way as that number is a real number. And now we can say that we can convert our complex number is now going to be an a plus a b by I, where both a and b are real numbers. So technically we have sort of simplified the conceptual problem of the imaginary numbers by just talking in terms of a unit of imaginary multiplied by a real number. We do the same type of thing in vectors, where you may have a particular vector which we can easily call v, and we can say that that's actually equal to the magnitude of v multiplied by the unit vector in the line or the direction of v. So again, what we're doing is we are separating out a sense of magnitude from a sense of what the item is, the unit vector in a certain direction. Here we're doing the same thing. We have so much of a simple, yes, we can understand it, real numbers, and we're saying I have a real number times this one very curious item which is called I. What's the algebra behind that we deal with in this? Adding them is awfully easy. If we pick two of them, to add them, you just add the real bits, and you also add the imaginary bits, taking one away from the other. It's the same thing. You look at this side and you'll get a 1 plus, and now you look at this side, 1 plus 2i. Now, I don't know about you guys and how good your handwriting is, but mine's atrocious. And I have, and you will notice it here, a 2 that looks quite similar to my lowercase I here. Because of that, I am very careful to put in the dot over my I. And you will notice that in all of the examples on this page I do my I like this with a dot. If I write a lowercase j, I'll always write lowercase j with a stroke through it, in the same way as I'll draw a 7 like this, because I'll often write 1 like that, and I don't want to get confused, so I'll put a stroke through 7 and a lower j, and I'll always put a dot over my I. So if you're trying to decipher my handwriting, and more importantly, and worse still, if you're trying to decipher your own handwriting later, or if some examiner is trying to decipher your handwriting, you have to give them at least some help. And the help I'll give is a dot over my I. And something like that will probably work for you too, unless you have very good handwriting. So then, let's look at algebra again, and we will talk in terms of two numbers. That's a binomial multiplied by another binomial. And you will know well from that it's first by first, first by second. We'll just to remind you. Second by first and second by second. So you'll say AC plus AD plus BC plus CD. Standard. Well, it's the same thing we do with complex numbers. Now the interesting thing is, here now we're going to get into an interesting switching out of complex numbers or switching back into complex numbers, because we know that this little I thing, which we have written up here, look at them, we know that that I is equal to the square root of minus 1. Because of that, we can say then that implies if I squared the I by I will be the square root of minus 1 multiplied by the square root of minus 1, so it's minus 1. So that's, sorry, I squared. And also I cubed, which happens to be I by I squared. That's so we can use the lesson we've just learned. It's going to be I by minus 1, so it's minus I. And I to the power of 4, it's I squared by I squared, which is minus 1 by minus 1, which is 1. So I is just the root of minus 1, I squared is minus 1, I cubed is minus I, and I to the 4 is 1 again. Now obviously I5 just starts back the cycle again. It's 1 by I, so it's I. There's only these 4 that we're looking at. The I is this, the I squared is that, the I cubed is this, and the I to the 4 is just 1. Once we keep that in mind, it's very easy to multiply these numbers. And we'll, just to begin with, we will do it the exact same way we did it over here, and then I'll say to you it's actually easier in complex numbers to do it slightly different. So we're saying 1 by 2 is 2, and 1 by I is I, and we're saying 2 by 3i is 6i, and now we're looking at plus 3i by I. And if we look at that, we're saying, whoa, that thing is minus 3, because the I by I is minus 1. The interesting thing you need to notice is that one and that one has given us complex numbers, whereas the first by first and the last by last have both given us a simple real number. So it's actually easier if we are multiplying out complex numbers to do first by first and last by last. So we'll go 1 by 2 plus the 3i by I, and now you do the remainder of it, plus the I, which is 1 by I, plus 2 by 3i. Because now what we're going to get out of it this way, you're going to get 2 minus 3, which is real, plus, and all of these will have i's, so 1 plus 6i. So now we're saying it's minus 1 plus 7i. Straightforward enough. There is an interesting little lesson that comes out of this. You will have noticed that I've often emphasized the importance of something that I'm going to show you again, because it's so important, and it is the difference of two squares The algebra chapters, the very first algebra chapter, will also give you the difference of two cubes and the sum of two cubes, but they actually don't give you the sum of two squares. And you might have been curious about that. The answer is the solution is going to be a complex number. Okay? What would it be? Well, as it turns out, so now if we were to say x plus, and we leave it at 3, x squared plus 3, we're saying what are the roots of that, or the factors of that? We can say it's x minus 3i by root 3i by x plus root 3i. It's a nice easy one to remember, and I'm saying to you, memorize it in the same way as you should have memorized this one and the sum of two cubes and the difference of two cubes, because every time you memorize things like this, it'll speed you up in your exam, and being fast in the exam is important because time is your enemy, unless you get ahead of the curve, of course, and that's the idea. So then, we're now saying addition is simple, subtraction is simple. Multiplication is straightforward, you just watch for the I by I business. And how about division? Division, again, I have deliberately talked about this because it also comes in for division. If we have, for argument's sake, what do we do with that? What we recognize is to get rid of this rational expression, to simplify the rational expression. We can see this as being one of the conjugate factors of the difference of two squares. Now then, we have known from our algebra, and look it over here, it's just this. These are the two conjugate factors. So at the moment we can say, look at our first bit, and this time we have a plus in here, and our second bit. So what do we multiply? We can multiply anything by 1 without changing it. So this rational expression here will get multiplied by 1 in the form of something divided by something, and it's going to be the conjugate of the number underneath here. So it's going to get multiplied by 3 minus 2i and 3 minus 2i. You will notice they just divide each other, so we're only multiplying by 1. Now what we've done is we've converted the top into a multiplication. And I want to come over here just to talk about the bottom end of it. Okay? 3 plus 2i by 3 minus 2i. And we'll do that out over here because you should never have to do this again. You should be able to go without the multiplication bit, be able to do the answer. So let's look at it. 3 by 3, and we'll go last by last, like we said already. Minus 2i by 2i, and now we will go plus 3 by 2i minus 3 by 2i. We can see now that the I bits here have cancelled each other out. Okay? We can also see that that I by that I is going to give us a minus 1. And minus 1 multiplied by this minus here will give us a plus. So that is equal to 9 plus 4. So we could say over here, yeah, it's all over 9 plus 4. So fundamentally what we're saying is a plus bi by a minus bi equals a squared plus b squared. So you don't have to bother with a multiplication down here once you know this by heart. I am saying to you that many times that this is really important, and now this particular one, which is the sum of two squares, which has got two complex conjugate roots, can also be looked at in reverse, where we're looking at a division problem and you now bring in the conjugate of the lower number, and now you don't bother multiplying them out because you know what the answer is going to be. It's the first number squared plus the real part of the second number squared. You've actually made quite a few pages through this at this stage, so you should be heartened by that. Now, that's basically the mechanics of how to deal with these numbers, okay? What can it do for us? Or what other issues do we have to address? Now, if we look at a real number, we're well within our rights to inquire as to what the square root of it would be. So how about the square root of complex numbers? The example that's given in this particular book is, let's look at the square root of minus 5 minus 12i. Now, do you know the answer to this? And you aren't supposed to know it straight off. You're supposed to say, no, I don't know the answer to this. And what we always do in maths is we name it. We're going to say, well, whatever complex number the answer is can be written in this form. Now, this form here can be used and manipulated as though we did know the answer. We're saying, if that's the square root of this, I can square both sides. And I'll say minus 5 minus 12i is equal to a squared. Now, remember, come over here and we'll do it out the long way for you. A plus bi. We want all the real bits together, so we will go, this will give me a real bit, and that will give me a real bit. So we'll get a squared minus b squared, because b by b is b squared and I by I is minus 1, so that's going to be our real bit. And we're saying plus what? We're going to go a plus bi and a by bi to a b I. Now then, what we can say now is, the only way that this expression that we're looking at here, this equation, can be true is if this real bit is equal to this real bit, and similarly this complex bit is equal to that complex bit, the imaginary bit. That implies a squared minus b squared must be equal to minus 5, and 2ab must be equal to minus 12. Like in so many problems that we get, not just in Leaving Cert maths, but right through, you'll often finish up with two simultaneous equations, and once you get that far, it's easy. In this case here, we'll use the second one to find an expression for a or b, and we'll substitute it up into the top one. Okay? The results that come out of this particular thing have to be checked, because we have to confirm that the results we will get will live up to what we have set up here. We've said this is a complex number. What does that mean? It means that the a and the b must be elements of R. They must be real numbers. And down at the end, we have to get a solution, and we check, or we'll often get two solutions because you'll finish up with a quadratic here, and now you check them. And when you check them, you can generally find that one of the solutions does not fit, because it won't be a real number for A or B. And once you do that, this is an easy job. So let's look at the example that's given in this book. Now notice how these things are exactly the same as before. Pretty obvious, okay? And we're saying, right, don't I know a number of things? A squared minus b squared is equal to minus 15. Name your equation, because remember, your exam document is a communication one. And if you don't communicate well, you can expect to lose marks. So you name your equations. And we're saying 2ab equals 8. Now what we will find from this is that b is equal to 4 over a, which then implies that we get to substitute it in to equation 1, and you'll get a to the 4 plus 15a squared minus 16 equals 0. Now this is still a quadratic, because I can imagine a number c which is equal to a squared, so technically you say that's c squared plus 15c plus, minus 16. And now we're saying, okay, well if that's the case, I can now factor it like that. So I can say a squared minus 1 by a squared plus 16 equals nothing. And this is the whole issue here. Watch what happens. That implies a squared equals 1, or a squared equals minus 16. You would think, great, lovely, they're nice looking numbers. But now what would happen when you get a equals the square root of minus 16 over here? And that's not valid. You cannot do that, because the square root of minus 16 means that we're back into imaginary complex numbers, and we set up our problem up here as an ordinary complex number, which is a real bit plus a real bit by I. So the only one that gives us a valid answer down here is this one. A is equal to, now, plus or minus 1. And after that, it's an easy enough matter to figure out what solutions you get out of this. That's how you find out the square roots of these things. And it's actually nice to know that complex numbers have roots, square roots, which are complex. So this is a very complete system here. Complex numbers always give you your complex numbers. So these guys have a lot of validity. They're a closed set of numbers. And as you progress through college, you will actually find that the amount of solutions that depend on complex numbers is staggering. A lot of modern engineering and science just wouldn't be there if we did not accept the imaginary part of complex numbers. So while we don't know what the square root of minus 1 is in real terms, we can see it as our little imaginary friend that helps us with all of these complex numbers. Now let's look at complex equations. Let's look at a quadratic. Before, what you will have noticed is we had one earlier which looked like this. That's some function of x. Now the main thing I want us to change, now that you're getting used to these things, as a tradition, we'll say. The tradition is that when we're talking about real numbers in algebra, we'll use x's and y's and z's. When we're dealing with complex numbers, we'll normally use this. It changes to this. And if we're looking for the roots of that particular equation, we'll set it equal to 0. So that's z. Now, because it's the last letter in the alphabet, if we happen to be talking about 2 or 3 different numbers, we don't have anything after the z, so we'll have z1, z2, z3. That's the way the system goes. What you will notice about this particular one is technically there's a 1 here, so that guy, technically the -1 here and this, they're all real. And even though they're all real, in quadratic equations you can actually get roots which are complex. They have an interesting characteristic about them, and the characteristic is that while all of these three are real, if one root is complex, the other one is its conjugate. Whereas if we had a different type of an equation, such as and we want to get the roots of it, what you will notice is that guy isn't real and that guy isn't real. They're both complex. When an equation has any one of the three, either on the x squared, the x, or the free number, if any of the three is not real, if it's complex, and even if it was only a little itty bitty I, what we can say is that the roots are not conjugates. Now, again, just to remind you of what a conjugate is, a plus bi, that guy, and a minus bi. They're a conjugate pair. And as we've talked, if I multiply those together, that's just a little revision. Now we can use the standard solution of the quadratic equation, you know, the minus b plus or minus the square root of blah blah equation. We can use that to solve these things. Now you'll generally finish up in a nice interesting little position. For example, you will do your usual ax squared plus bx plus c on the right hand side and go x equal to minus b plus or minus. Write that over there because that'll give you the map as to what you're doing. But what you will get out of it is that z is equal to minus 4 plus or minus the square root of 16 minus 52 over 2. And I'll run across the page here. You'll have to forgive me for that. The first thing I would say to you, I always like to simplify down before I start dealing with messier stuff. Now clearly the 4 will be able to be divided by the 2, and I would look very quickly for a factor inside in here. Now 4 4s are 16. 4 by what is 52? Okay? Just messing with your head. So we're saying it's equal to 2 plus or minus the square root of 4 minus 13. Okay? I've just pulled out the 4, a factor 4, a common factor from the numbers inside, pulled it outside the square root so it became a 2, and now all the 2's disappear and life gets easier for us. But what it means is that the answer here is now a situation of 2 plus or minus. Now 4 minus 13 is how much? Where we have to be a little bit careful when we're dealing with these problems is where we haven't been given a value of one of the coefficients, because invariably what's going to happen is you'll finish up with some expression in here and we want to get the square root of it. Okay, the expression in here can be a complex one. We could have got in here, well, maybe it's the square root of 3 minus 2i, while we still have our minus b plus or minus over 2a here. And what you do is you separately look at this, okay? Because remember, we've already looked at finding and figured out how to find the square root of a complex number. So we will treat that independently. We'll go to the side of the page, work out what that square root is, and we'll parachute it back into the equation. So it's just a slight extra complexity, but nothing more than that. Okay then, this chapter, as it's laid out, brings us on to more complex equations. What does that mean? It generally means, like in the algebra, that you're not going to be told what a coefficient is and you'll be given a letter instead of it. Now, for these kind of questions, you can be asked to do other things. In this case, it says, 3 minus 2i is a root. Now, we could have been told that z minus 3 plus 2i is a factor, right? We could be told that. Now, do you remember the factor theorem in algebra? Well, what you should be noticing is that all we've been doing actually all along here is playing around with algebra. This is just algebra, but it's algebra where numbers can be complex, in other words, have an imaginary bit to them. But all the rules are fundamentally the same. The factor theorem applies. So if we were told this was a factor, and if we were dealing with a cubic and it says, oh, prove that this is a factor, all you would say is, okay, I'll find what the root is, and I'll plug in the root into the equation, and once I get an answer 0, I'd say, perfect, yes it is. Now, again, as in the algebra situation, if you were told, prove that it is and find the other roots, you generally don't plug in the root. What you'll do is you'll use the factor, you'll do your long division, because you want to simplify down your equation and find the other roots. It's a bit similar when you have got things like an unknown here, okay? You expect to do a long division and things like that. We are now saying to ourselves one other thing, and that is what we've discussed. There is an I up here. There's also an I here, a minus I actually. Those I's tell us that even though this is a root of the equation, that 3 plus 2i is not a root of this equation. How can we prove that? It's actually quite easy. Let's say that we have an A plus BI and that A minus BI, this conjugate pair, that they are actually roots to an equation. We can multiply them. And when we multiply them, we're just going to get A squared plus B squared. And we can also add these guys together. Now, when we add these two together, this one and this one will disappear, so we're left with 2A. And you know from your algebra with just real numbers that what we actually have is a situation of for the complex numbers, it's going to be z squared minus 2a z plus now what you will notice is that the free number, the a squared plus b squared, is real, and that's real. So we've basically shown if there are two conjugate roots that the equation that's formed from them has, and obviously this is a real number, just one, just has real coefficients. That problem up at the top here, because it has got an I here and an I there, or any one of those, you only need one to not be real. It can't have conjugate roots. So if we get any form of equation which has got nice easy numbers to it, okay, let's say in the case of the example given here, x cubed plus z cubed plus a z squared plus b z minus 65 equal to 0. We're trying to find the roots of this thing, and if we're told that a and b are elements of R, they're real, what we're now saying is that number, that number, that number, and that number are all real. We expect that there'll be a conjugate number, two conjugate numbers, complex numbers, that will be roots, and the third one will be a real root. So if we're given any one of those conjugate numbers, okay, we'll say 2 minus 3i. We would also expect that 2 plus 3i is a root. And what you can easily do is you can say z minus this and z minus that will be my two factors. So I can multiply those two together and I will get a z squared minus 4z plus 13. Now please notice again, real, real, real. Why? Because that and that are conjugates. Conjugate roots produce quadratic and cubic equations, etc. that are or have the characteristic that each of the constants are real. Now that we've produced this, we can simply divide this into the cubic, and we can also substitute each of these numbers in here too. Well, any one of them would basically do for us. We'll substitute in that guy here. We'll get an expression in terms of a and b. Then we will substitute this guy in. We'll get something in terms of a and b. So we'll solve for a and b. And after that, we can divide this into the equation and you find the third root. It's exactly the same kind of play that we had for ordinary algebra with straightforward real numbers. The only thing excuse me, to keep watching for is to understand that we've one new rule or theorem here, and that is the conjugate root theorem. If they've told you that one root is, like in this case, 2 minus 3i, but if they don't tell you that the a or the b are real, you cannot really, in my opinion, you can't assume the conjugate. You have to know that the equation is set up in such a fashion that all the coefficients are real. If you know that, now you can appeal to the conjugate rule theorem, and you can bring in the second one, produce a quadratic, divide it into the cubic, and find the third factor. All easy games. Once you've got that, everything else is exactly the same. The only way they can complicate up the problem a bit for you is to bring in little variables like, oh, there's an a, or sorry, not variables, unknowns, an a coefficient and a b coefficient unknown, exactly the same way as it was done in the complex numbers with, or sorry, the algebra for real numbers. You can play the exact same game with these. For example, you know, for the alphas and betas for the roots. If we were saying alpha and beta are the roots, and it'll say in this example here, express in other words, express it as a complex number. Okay. Now what do we know about these things? Notice how the same toolbox is coming in here as was coming in and when you learnt it in the algebra, because we can immediately replace the alpha squared plus beta squared with an alpha plus beta squared minus a 2 alpha beta. And obviously what we're basically looking at is a situation of z squared minus outside of alpha plus beta z, okay, plus alpha beta. Same setup, only we're saying z now instead of x. Any time that we're given an expression and they say, oh, express this in such a form, or they tell you some things about the roots, the whole reason we replace this guy with this is whether it's alpha squared plus beta squared or an alpha cubed plus beta cubed or anything like that, we're looking to find an expression which only contains alpha plus betas and alpha beta, because those we can know straight off from the equation that we had. That's just simply subbing in from here. We know the alpha plus beta. It's that guy, because we're dealing with minus the alpha plus beta, so it's minus 1 plus I. The 1 plus I must be the alpha plus beta. That's why it's sitting in here. And the alpha beta is the free number, which includes all of this, which is there. And obviously the minus 2 just belongs to that equation up here. It just comes from that. The games are the same. I've often thought that complex numbers, at least the first half of the chapter, should not be taught separate to the algebra of real numbers. I actually think it should be included in it, because when you're going through the algebra of real numbers, you're actually getting an incomplete understanding of quadratic solutions and cubic solutions. You're never really brought into the know of that the square root can actually be a negative number. Now, other than that, we just need to recognize two little things about it, and then I'll let you go. In algebra, real numbers, we got very used to plotting x versus y. And you could say if that's 2 and if that's 5, that point is 2, 5. We can also plot complex numbers, but we can't, like oil and water, we can't mix the real part with the imaginary part. So we draw something quite similar. Only this guy, instead of being called x, is the real bit, and this one is the imaginary one. In the same way as the real one can be counted out, the imaginary one can be counted out. But remember, the basic unit in the imaginary ones is I, 2i, 3i, and similarly down along here, minus I, minus 2i, minus 3i. Now we get minus 1, minus 2, minus 3. So if I have a complex number which is 2 plus 3i, I'd expect it to be here. This one down here, I would expect to be minus 2 minus I. Very straightforward. What else do we need to know? The last little point, remember I told you there was 2. I might actually want to know what that length is. Now, we've faced this problem in a number of other chapters, including vectors, where we wanted to get a modulus, an actual length of something. We have looked at it obviously in geometry, where you want to get the distance between 2 points, or particularly between a point and the origin. And you'll notice as soon as we've drawn that red line there, that this blue line, that's the mark for 2, by the way, that blue line and the blue distance out here means we've formed a right angle triangle, and we can appeal to Pythagoras. So if this number here is a, b, I, we will say to ourselves, okay, a squared plus the length in the imaginary side, which is b squared, has to be equal to, we'll just call it L for the moment, yeah, squared. Now, the square root of a squared plus b squared, which we're now saying is L, that length, and we want to give a name, a meaningful name to this. If that particular number here that we were using was z, which is the a plus bi, we'll say to ourselves this symbol, which is the same symbol as we've used in vectors, that we're using in geometry and algebra, only we're doing it now for complex numbers. We're saying this guy has a length, a modulus, same name, and it's got by appealing to Pythagoras, setting up a right angle triangle. We break complex numbers at this point because the chapters now proceed into showing you, the same way as it actually did in geometry, that we can express a number such as this one over here. We can show it by coming out so far and going up so far, or we could express it as a length and a rotation, which is a polar coordinate system. Because it's intrinsically a different way of kind of looking at the world, where it's a length and a rotation rather than two lengths which are perpendicular to each other, and because much of the mathematics that is used in it has to do with trigonometry, that section is best left and separated out until you've covered trigonometry. So I've split the chapter into this first half, which I've brought you very slowly through, I know. This first half is just so as to let you know that complex numbers aren't all that complex at all. They just have a second bit, and that second bit has been tamed to being a real number, a magnitude times one little unit, which we'll call I. It's the single standard unit in the imaginary side of things, and it's the root of -1. And almost everything follows the same as you have been applying already in algebra, and even, as you can see towards the end here, in geometry. So this isn't a problem for you. All the basic rules apply. We just add one more, which is to recognize that if all of the coefficients are real, then if there is a complex number as a root, its conjugate will also be a root. And there's just the simple proof of, adding the two complex roots and also multiplying them together to show you that you only finish up with real bits. If you were to get caught out, it'll only be because if an unknown coefficient is brought in, that you just get caught on a long division or some little bit of basic algebra. You won't get caught because it's called complex numbers and because of the little imaginary bit in it. This is a very easy half of a chapter, but for you and for your next few years when you're in college, this is a base that is really important. To understand complex numbers is to open out the massive fields of physics and many other disciplines, including engineering. So I'll leave it at that, and I will see you the next day. Goodbye now.